Hi everyone, I'm Aryan and I'm going to tell you about why linear Matroid intersection is in catalytic log space. This is joint work with Yaroslav and Antoine. So let me start by defining linear matroids. Let A be a matrix of size m times n and let S be a subset of 1 to n. S is defined to be independent in A if the set of columns with index in S are linearly independent. And the linear matroid corresponding to A is this independence structure. So it's a tuple where the first part of tuple is the base set. So it's the indices of the columns in the case of a linear matroid. And the second part of the tuple is a family consisting of all the independent sets in A. Okay? Now let me tell you what the linear matroid intersection problem is. So the problem takes as input two linear matroids A and B, and the goal is to output the largest set S, which is independent in both A and B. And any such set S is referred to as a common independent set of A and B. Okay, this is just terminology. Good. Now, why is linear matroid intersection interesting? The reason is that it's a generalization of many problems. And just three examples are maximum bipartite matching. I'm assuming most people are familiar with this problem. The next is rainbow spanning tree. So in this case, you have a graph where the edges are colored. And as output, you want to produce a spanning tree where all of the edges in the spanning tree have different colors. The third is edge disjoint spanning trees. So you're given a graph as input, and you want to produce two spanning trees which are edge disjoint. And there are many more problems, but these are just three examples. Good. Now let me tell you about catalytic computation. So in the catalytic computation model, a space-bounded Turing machine is augmented with a read-write catalytic tape. The catalytic tape is instantiated with some arbitrary data, which you can imagine as being chosen by an adversary. So it's the worst case data for whatever algorithm you try to design. Upon termination, the catalytic tape must contain its original contents, right? So if the catalytic tape is just empty or didn't have this condition, then you could just use it like free space and you would have, however much space this catalytic tape gives you, right? But this is the condition which makes the catalytic tape interesting. So now let me tell you about the class Catalytic Logspace. So catalytic Logspace is the class of problems decidable by a catalytic Turing machine with a logarithmic length work tape and a polynomial length catalytic tape. Good. Now, why should you care about catalytic computation? The answer for me is that it provides a clean model to study a poorly understood property of space. To tell you what this property is, let me ask you a question. What makes space a powerful computational resource? There's a standard answer to this question, which is that space can be reused, right? And this is what people typically mean. That you have, for example, two subroutines, Calvin and Hobbes. Hobbes was using some space, the hard disk in this case, but it's not using that space anymore. So Calvin can just wipe it clean and use it for its computation. The property that catalytic computation wants to study is, can space be borrowed? So imagine now that Hobbes is actually using some space. So it's not actively using it, but it's storing something important there. Okay? Now Calvin needs to compute something. So Calvin can use that space as long as it restores whatever's written on it right now. Right? So imagine that Hobbes is giving Calvin a hard disk, which is completely full, and Calvin has to give it back to Hobbes exactly how it is. And Calvin is so confused about whether he can do anything with it, right? And the point of catalytic computation is to tell you that you can do something with this hard disk, right? So it turns out that borrowing space can actually be a pretty powerful tool when designing space-bounded algorithms. And an example is the tree evaluation problem. This problem was originally conjectured by Steve Cook to require log squared in space. However, using techniques from catalytic computation, Cook and Mertz solved TEP in log n times log n space. And this TEP algorithm was recently used by Ryan Williams to show that any problem which can be solved in time s can be solved in space approximately square root s, right? So this idea of borrowing space is actually unlocking completely new tools in space-bounded algorithms. Good. Now, what's known about CL? I'm going to tell you about CL with respect to four classes: NC, TC1, NL, and L. Okay? If you don't know what these classes are, then don't worry about it. So the first thing is that L is obviously in CL, right? By definition, because a CL machine has a logarithmic length work tape available. Now, in the paper which introduced CL in 2014, it was shown that TC1 belongs to CL, right? So this is a really cool result. And it already shows that CL is somehow much more powerful than L. And then for the longest time, there were no more inclusions, okay? So it was conjectured that CL might belong to the class NC. Now, recently, there was a big barrier shown to this conjecture by the result that bipartite maximum matching belongs to CL, right? And importantly, bipartite maximum matching is a problem outside NC, and it's a big open problem to show that matching is in NC. Okay, so this forms a barrier to the conjecture that CL might be contained in NC. In this work, we strengthen this result by showing that, in fact, linear matroid intersection also belongs to the class CL, right? And linear matroid intersection is, in particular, is a generalization of bipartite matching, right? So this is a strengthening of the previous result. Good. Now, let me give you a quick idea of the framework we use. So this framework is called compress or random, and it does exactly what you think, okay? So, like I said earlier, just given a catalytic tape, right? Just given a hard disk which is completely full, and you have to return the way it is, it's totally unclear how you can use this hard disk. So here's the idea. We try to run a randomized algorithm using the catalytic tape as the source of randomness. Okay. Now, of course, the catalytic tape is not random, right? So it might fail. But if the algorithm fails, meaning the catalytic tape contains bad randomness, then we know that the catalytic tape contains a really specific string, right? It's not random, it's very specific. And using that specific structure, we can try to compress the tape. And that's exactly what we do. Okay? So let me tell you how to do that. Let me tell you two algorithms for linear matroid intersection. The algorithm on the left is by Lawler, and the algorithm on the right is by Narayanan, Saran, and Vazirani. Okay? I'm not sure if this is a presentation that Lawler used because I picked it up from a textbook. So it starts by initializing S0 as a common independent set of size 0. Now, for k increasing from 0 to n minus 1, it constructs something called the exchange graph of Sk. Okay, so this is a directed graph, and it can be node weighted, can be unweighted, depending on how you use it. If you don't know what this is exactly, don't worry about it, but you can find it in any standard textbook. And you should think of this as maybe the analog of the residual graph in matchings and flows. Okay, so it's essentially the same kind of object. Now, the algorithm searches for an ST path in this graph. If no path is found, then it turns out that Sk is a maximum common independent set, so we have our answer. And otherwise, it turns out that Sk augmented with P is actually a common independent set of one size greater. Okay? So either we find the maximum common independent set or we increase the size by 1. Now the other algorithm, the algorithm of Narayanan, Saran, and Vazirani, is very different. Okay? So it starts by sampling random weights. Then they show that with high probability, for all k, the minimum weight size k common independent set is unique under W. So this is the isolation lemma. Finally, they give an algebraic TC1 algorithm which outputs the unique minimum weight size k common independent set, let's say Sk. Now, as we discussed earlier, TC1 is contained in CL, so this is actually a CL algorithm. Good. Now, here's a succinct version of what I just said, right? The algorithm on the left starts with S as an empty set, And while it's not maximum, it increases its size by 1 using reachability. The algorithm on the right samples random edge weights. With high probability for all k, the minimum weight size k common independent set is unique, and there's a CL algorithm which outputs it. Now, both algorithms have some parts which make it good for CL and some parts which aren't. So in particular, let's look at the algorithm on the left, right? So it starts with an empty set, which you can definitely do in CL. And each step which increases its size can also be done in CL, right? Because it's just reachability, which is in NL, which is in CL, right? Like we discussed earlier. The part that we can't do in CL is this n-step iterative process, right? So the bad part is it has this n-step iterative process, but the good thing is that the local steps are really easy and clean. Now for the algorithm on the right, the thing that we can't do is sample random edge weights, right? Because we have no randomness. But given good edge weights, the actual CL algorithm to output that common independent set, is doable in CL, of course. So the problem with the algorithm on the right is that it needs randomness, but the good thing is that it can construct a large set in one shot. Now what we're going to do is apply the compress and random framework on the algorithm on the right. Okay? And when the algorithm fails, so when the randomness is bad, we're going to try to use the local steps of the algorithm on the left to compress the catalytic tape. So let me tell you how that works. So I'm going to describe the solve/compress algorithm. So this algorithm either solves LMI, linear matrix intersection, or it compresses the catalytic tape. Here we go. So the idea is that we use the string on the catalytic tape as the random bits for the NSV algorithm. These are the weights W. If it succeeds, we're done, but let's assume it fails. Then we just find the smallest k such that the NSV algorithm can't construct a size k plus 1 common independent set. Okay? And such a k necessarily exists because k could even be 0. Okay? Now, we use 4 subproblems, which I'll describe on the next slide, to compress the edge weights W on the catalytic tape. Okay? So let me tell you about the 4 subproblems. So given as input 2 linear matroids A and B, an element E, right, so a column E, a weight assignment W, so these are weights on the columns, and some size K. So note that K is not a column, but rather a size, okay? And so given these things which satisfy the property that the minimum weight size K common independent set is unique, the 4 problems are as follows. We want to compute a minimum weight size K common independent set containing E. To be clear, what this means is that out of all of the size K common independent sets which contain E, we want to compute the one of minimum weight. Similarly, out of all the ones not containing E, we want to compute the one of minimum weight. And then for the last 2 problems, everything is the same but of size K plus 1. Okay? So essentially, we just want to fill in this table, right? Size K plus 1, and containing E and not containing E. So the first thing I'm going to show is that the first 2 problems, the ones in the top row, are equivalent, okay? So given a size K common independent set containing E, we can find one not containing E. And the idea is fairly straightforward and pretty similar to what we could do in the case of bipartite matching, right? So if you don't have intuition for linear matrices, just think about bipartite matching, and it's essentially the same idea. So step 1 is to compute a node-weighted exchange graph of A and B with respect to S. Okay. Then we compute a minimum weight cycle C containing E in this exchange graph. This step can be done via a reduction to minimum weight bipartite matching and then just applying AM25. Finally, we can just output the symmetric difference of C and S. Right? So this doesn't show equivalence, by the way, but the other way around works exactly the same way. Okay? So given one not containing E, we can find one which contains E by doing exactly the same thing, computing the exchange graph, finding a minimum weight cycle, and then outputting the symmetric difference. Okay. So this idea shows that both of these problems are equivalent. And now I'm going to show that if we can find a size k common independent set not containing E, we can find a size k plus 1 not containing E. Okay. So that problem 4 reduces to problem 2. Okay, so given a minimum weight size k common independent set not containing E, we can find a minimum weight size k plus 1 common independent set not containing E. Now the idea is that we compute linear matroids A prime and B prime whose common independent sets are exactly the ones of A and B not containing E. Okay. Then we compute the node weighted exchange graph of A prime and B prime with respect to the set S. Similar to Lawler's algorithm, we compute a minimum weight path P in this exchange graph and then just output S symmetric difference P. Okay, so this is not similar to, this is exactly Lawler's algorithm after you compute A prime and B prime. Good. And exactly the same idea also shows that the same implication on the other side. Okay. So all of this shows that solving either of these two problems is sufficient, right? And just note that we have edge weights such that the minimum weight size k common independent set is unique, right? That's given as input. And then just applying the NSV algorithm, we can actually find that common independent set. Okay, so we can find Sk. And note that Sk either contains E or it doesn't contain E, right? It has to lie in one of the two boxes, right? So we always solve at least one of them via NSV, right? And so we can actually solve all of them. And something we show in the paper is that we can actually solve all of these even when we're not given the weight of E itself. Okay? So imagine that W is a weight function from all of the other columns, right? Or on all of the other columns, but not on E itself, right? And note that all of these cells in this table are still well defined, right? Because if you have two sets which both contain E, then you can compare their weight even if you don't know the weight of E itself, right? And similarly, if you have two sets which don't contain E, then you can compare their weight even without knowing the weight of E itself, okay? So we can actually solve all four of these problems even without being given the weight of E, which is going to be important for us. Okay, good. So now let me tell you how the fourth step works. How the third step works. So remember the situation we're in. We know that the minimum weight size k common independent set is unique, and the minimum weight size k plus 1 common independent set is not unique. What we're going to do is find E, which occurs in some, but not all minimum weight size k plus 1 common independent sets. Okay? And such an E is called a threshold element. Okay? Now, how are we going to do that? Well, we're just going to iterate over all columns E. Okay? And we're going to check if it's a threshold element. How do we check if it's a threshold element? Well, we know how to find the minimum weight common independent set of size k plus 1 containing E and the one not containing E. Okay, this yellow and orange thing respectively. Now, it's easy to see that E is a threshold element if and only if both of these things have the same weight, right? And because we can solve both of these problems, we can check if they have the same weight. And so we can check if E is a threshold element, and so we can even find a threshold element, right? So let's say we found a threshold element E. Well, this equation here gives us a good idea of how we can compress the tape, right? Because we can write the weight of E as the difference between this orange set and this yellow set, right? The weight of the orange set and the weight of the yellow set. Okay? And that's the idea. We simply erase the weight of E from the catalytic tape and replace it with K. Now K is from 1 to n, so it only takes log n bits, whereas the weight of E could be up to n to the 10, let's say, so it takes 10 log n bits, right? So by replacing the weight with K, we save like 9 log n bits. And really all we need is that we save at least one bit. So this is compression. Okay, what about decompression? So let me tell you how we find the weight of E now. So let E be the threshold element whose weight is compressed to K. Using problems 3 and problem 4, which we can do even without the weight of E, and we don't have the weight of E, so we need to do it without it, we compute the minimum weight size k plus 1 common independent set not containing E and the minimum weight size k plus 1 common independent set containing E. Okay? And now we just set the weight of E so that both of these sets have equal weight, right? We knew that they have equal weight before, so the weight of E must have been this. And that's it, that's the decompression. So our final algorithm now is as follows. Each step of solve/compress either solves LMI or compresses the catalytic tape. Thus, we just run this algorithm polynomially many times. If it solves LMI, we're done. Else, it frees up at least polynomially many bits on the catalytic tape, at which point we can run any polynomial space algorithm, right? We could run Lawler or we could run NSV, whatever you want. And at the end, we can just run the decompression algorithm. So that's it. That's our entire algorithm. Here are some open problems. I don't think I have enough time, so I won't talk about them, but you can pause the video here. And thank you for watching.